So if you've ever touched anything related to electronics, you've definitely heard of Kirchhoff's laws. I mean, there's the absolute foundation of how we analyze circuits. But let's be honest, sometimes they can feel a little weird, right? They don't always click with our gut feeling of how electricity should work. And that leads to a really, really good question.
It turns out, even the most basic, fundamental laws can be a bit confusing, and when our own mental model of how something works is just a tiny bit off, these laws can feel like they're totally wrong. That's the exact problem we're going to untangle today, and it all starts with a question that, honestly, most of us have probably wondered about at some point.
This question, right here, it's straight from a Reddit forum for engineers. And it's perfect, because it just gets right to the core of a super common misunderstanding. The person asking kind of knows they're probably mistaken, but their logic, to them, feels solid, and they just can't spot the flaw. So let's actually look at their reasoning.
And you know what? That is a fantastic question. It creates this mental image of electrons getting, stuck in a component, kind of like cars getting stuck in a traffic jam. So if some get stuck, then of course the number coming out can't be the same as the number that went in, right? It seems like it has to violate one of the most basic rules. So what are those rules anyway?
Okay. So let's dig in by making sure we're all on the same page here. Before we can figure out if the laws are wrong, we need to be absolutely crystal clear on what they actually say. And there are two of them, one for current and one for voltage.
First up is Kirchhoff's current law, or KCL. Now, the formal textbook definition says the algebraic sum of currents entering any point or node is zero. But a much simpler way to think about it is just what goes in must come out. Whatever amount of current flows into a junction has to be the exact same amount that flows back out. No exceptions, none.
And this diagram just illustrates it perfectly. Look at that junction in the middle. You've got currents A and B flowing in, they hit that central point, well, they have to go somewhere, right? So they flow out as currents C and D. KCL simply says that the total of A plus B has to equal the total of C plus D. That's it.
Okay, so that's the current law. The second one is Kirchhoff's voltage law, or KVL. This one says that if you trace any closed path, any loop, in a circuit, all the voltage gains you get from things like batteries and all the voltage drops you get from things like resistors, well, they all have to add up to zero.
So for example, look at this simple loop. We've got two power sources giving the electrons a push. As you go around the circuit, that voltage gets used up by the components. By the time you get all the way back to where you started, the total voltage change has to be zero. It's kind of like walking up a hill and then back down. You end up at the exact same elevation you started from.
Now, here's the really crucial part. These aren't just some random rules that someone made up for electronics. They're direct consequences of the fundamental laws of physics. KCL, what goes in must come out, is really just the conservation of charge. You can't just create or destroy electric charge at a junction. And KVL, what goes up must come down, that's just conservation of energy. You can't magically gain or lose energy just by going around in a circle.
Okay, so this brings us back to the heart of the confusion that started this whole thing. Why does it feel like electrons should get stuck? Well, it's because our mental model is just a little bit off. And a simple shift in how we picture electricity is going to make everything click into place.
Here it is. This is the mistake almost all of us make when we start out. We imagine a wire is like an empty pipe. We hook up a battery, and electrons start to pour in one end, having to travel all the way to the other. But that's not what happens at all. The reality is that a wire is already jam-packed, totally swarming with trillions upon trillions of electrons. They're just not really going anywhere in particular.
And someone in that Reddit thread came up with this fantastic analogy. It's not about one electron making the entire journey from start to finish. It's more like a Newton's cradle, that desk toy. You apply pressure, that's the voltage, at one end, and that push is transmitted almost instantly through the entire chain of balls, causing a ball at the other end to pop out immediately.
The classic water analogy actually still works perfectly, as long as we remember the pipe is already full. So think of voltage as the water pressure coming from a pump. Resistance? That's just a narrow section of the pipe that makes it harder for the water to flow. And the current? Well, that's simply the flow rate, how much water is passing by any single point in the pipe at any given second. So let's circle all the way back to that original question. Do electrons get stuck? The answer is no, not at all. The entire wire is full. If you push 500 electrons into one end, that pressure wave instantly pushes 500 other electrons out the other end. The flow rate, the current, is exactly the same everywhere in the loop.
Okay, so the theory is one thing, but seeing is believing. Now that we've hopefully fixed that little mental block, let's see how this all plays out with a couple of real examples.
because applying these laws is exactly how we solve for all the unknown stuff in any circuit.
So here we go. We've got a network of resistors. We know some of the currents flowing around, but we need to find the ones flowing between the junctions. And to do that, we're going to use KCL, our what goes in must come out rule.
Let's start right here at junction A. We see that 3 amps of current are flowing in from the left. Now, of that, 1 amp flows out, heading towards the top. So, what's left to flow out towards junction B? Well, it has to be the rest of it, right? 3 minus 1 leaves us with 2 amps. Simple as that.
And you just keep doing that all the way through the circuit. Now we move over to junction B. We know we have 2 amps flowing in from junction A. We also have another 3 amps flowing in from the right. So both of those currents combine and flow out towards C. 2 plus 3 gives us a grand total of 5 amps flowing out. See? What goes in must come out.
All right, let's switch gears and try out KVL, the voltage law. We're back to this simple loop circuit, and our goal is to find that unknown voltage drop across the resistor, the one labeled Vx. Just remember the rule, the sum of all the voltages as we go around the loop has to add up to 0. So to use the law, we just need to take a walk around the loop and add up the voltage changes. Let's go clockwise. By convention, when you cross a battery from the positive to the negative side, it's a voltage drop, so we treat it as a negative number. First, we cross the 5-volt source, so that's minus 5. Then we cross the 7-volt source, another drop, so that's minus 7. Finally, we go across the resistor, which is a voltage rise in this direction, so we call that plus Vx. And the law says all of that has to equal 0. And from there, the math is about as easy as it gets. Minus 5 and minus 7 gives you minus 12. So for the whole equation to balance out to 0, Vx has to be positive 12 volts. The voltage used by the resistor perfectly balances out the voltage supplied by the sources. So, we've cleared up the confusion, and we've seen the laws in action. But why is this all so important? I mean, this isn't just about solving textbook problems. These 2 laws are the fundamental tools for designing and understanding pretty much every single electronic device that exists. So let's just recap the big ideas here. First, and most importantly, Kirchhoff's laws aren't magic. They come directly from the conservation of charge and energy, fundamental physics. Second, they are so reliable that they form the mathematical engine inside all modern circuit simulation software. And finally, while there are some super advanced exceptions for things like antennas with changing magnetic fields, for 99.9% of all circuit analyses you'll ever do, these laws are absolute rock-solid truth. Which really just leaves us with this one kind of mind-blowing thought. It's incredible to think that everything, from the smartphone in your pocket to the massive global communication networks, can all be understood and designed using 2 principles that are as simple as what goes in must come out and what goes up must come down. How is it that 2 simple rules of conservation can govern the entire unbelievably complex digital world we've built?